Howdy, today on Flippin Science we're looking at acquired immunity.
Immune system protects us from the outside world that would come in. Our bodies knows how to keep us safe. I'm glad it's there.
So here's the science understanding. Exposure to an antigen is required for acquired immunity. It can be acquired through passive or active processes. Then passive immunity may be acquired from maternal antibodies or antibody serums. And active immunity may be acquired through natural exposure or through vaccination. So I'm just going to quickly go through how antibodies are produced. So there's two different routes. In one route you have B cells that already have antibodies on the cell membrane. If they bond with the antigen on the pathogen, that means they become activated. When they become activated, they produce plasma cells, which produce more of the antibodies that match the antigen. And they also produce memory B cells, which are ready to remember the infection. In the second pathway, you have a macrophage eating the pathogen and then stripping off the antigens and placing them on the surface of the cells. That then bonds with a T helper cell, which we can see down here, and that helper T cell activates a B cell. And then again, the B cell produces memory B cells, but also plasma cells, which produce the antibodies in large amounts. So today we're going to go through in detail acquired immunity. So acquired immunity can be produced naturally or artificially, and by both passive and active routes. So there's four different options really. Passive immunity is where the immune system of the individual isn't producing the antibodies itself. So down here we've got some methods here. So you can acquire antibodies from breast milk or through the placenta before born, or by having antibodies harvested from another source injected into you. Active immunity requires the body to produce its own antibodies. And again, that can be done naturally or artificially. You will naturally produce your own antibodies when you've been exposed to certain pathogens, but also we can encourage that by having a vaccine. That encourages the production of your own antibodies as well. So passive immunity you can get quickly and temporarily by injecting antibodies that are being produced by another organism into the affected individual. Here's an example using tetanus. So you have tetanus toxoid, you inject that into a horse, you leave it in the horse for a week or two. You take some blood from the horse, and now that horse has produced antibodies to the tetanus toxoid. You take those horse antibodies and then you inject them into a person who's immediately at risk of tetanus, and then they'll be protected for a short amount of time because they have the horse antibodies floating throughout their body. Another way that this happens is by drinking breast milk when you're a baby, or when you're inside your mother's uterus, you get antibodies from the blood from your mother too. In both cases, you're getting antibodies from an outside source. It gives you good immediate protection, but only for a short amount of time because your body will break down the antibodies as well. And also your B cells aren't producing antibodies from the antigens that you've been exposed to. So what that means is you're not producing any by yourself. So this gives you good immunity, but only for a very temporary amount of time. So in active immunity, this is where your body is producing its own antibodies using those B cells that have been activated and produced plasma cells, which are producing lots and lots of antibodies really, really quickly. The way you get active immunity is either by yourself being infected by a pathogen or by being vaccinated. The response can take a little while to develop because you need to produce large amounts of antibodies, and that can take a little while, so it can take days or weeks. But the protection that you get provided to you lasts a long time, so it can be years or even a lifetime in some cases. So down here we have chickenpox. So many children used to get chickenpox when they were fairly young. It's caused by this varicella virus. You get chickenpox, you're infected and contagious for about a week or so. It's apparently quite itchy and quite bad. But then you get lifelong immunity because of the antibodies that your body produces because of that infection. Now, why are the antibodies important? Because they do this over here. If they stick to the antigens on the pathogen, then they can stop that from merging in your cells, for example. They can also cause the pathogens to stick together, and again, that makes them not useful. They can stick to antigens that are dissolved in your blood and then stop them from doing bad things. And also they can activate the complement system that leads to cells exploding. These three ways also encourage phagocytes, so macrophages, to come along and eat the interesting particles that the antibodies have stuck to. so you get the macrophage eating those things. So that's why antibodies are important. Here's vaccines, and we'll talk about vaccines now. There's many different types of vaccines. You can expose the body to dead pathogens, so you can inactivate the pathogens by exposing them to chemicals or radiation. What that means is you kill off the inside of the cell, but the outside remains intact, and the outside is the antigens that your body responds to. You can also have weak strains of pathogens, so this is called an attenuated strain. So the strain that you're infected with doesn't cause you to get sick, but the outside antigens are exactly what your body is looking for. You can also have just parts of pathogens, which is down here, so a little subunit. That's just an antigen bit that your body needs to look for, and by producing antibodies that latch onto that, you'll stop that from doing things. Inactivated toxins or of pathogens, so this is what happens with tetanus. Rather than injecting you with tetanus bacilli, the bacteria that cause tetanus, they inject you with parts of the toxin. Not the whole toxin, because otherwise you'd get sick, but little parts of it. And that way your body looks for the toxin and inactivates the toxin, so that stops it from working as well. In all of these cases, what your body is producing is lots and lots of antibodies and also memory cells, so that when you get infected again, your body knows what to look for, and that reduces the effect of the infection. So here's some examples of some of those common types of vaccine. So live vaccines aren't really used very often anymore because they're difficult to keep alive and they can be expensive to keep it going. So smallpox, for example, we don't really worry about vaccinating for that because it's been eliminated completely from Earth. Live attenuated vaccines, this is where the virus is alive, or the bacteria is alive, but is a very weak strain that doesn't hurt you. So measles, mumps and rubella are those types. Killed inactivated vaccines, this is where you're using chemicals or radiation to kill off the inside of the pathogen, but you leave the outside antigens okay, so that your body can react to those. So here's some examples, so typhoid, plague for example. Toxoids, so tetanus, like I said before, where rather than injecting you with a bacteria, they just inject you with the toxoid, the bit that causes the issue to your immune system. And that way your body gets used to that. Then you have bits of cellular fractions. This is where you just mash up the pathogen, so the antigens are exposed. So hepatitis B, for example, is done by that. And just again, I'm going to emphasize that vaccines do work. And all of these graphs show how vaccines can work. So here we have pertussis in the UK from 1940 in this case and 1966, all going through to 1997. So mass immunisation against pertussis started here, and we can see as soon as that mass immunisation started, we get a drop in the cases of pertussis happening. And then we get a bit of a peak again. That peak can be explained by what happens over here. Here we can see that the amount of vaccination for pertussis decreased down to 30% from 81%. So when that decrease happened, we started to get increases in the amount of people getting pertussis. So then the vaccination rate increased again, and then we dropped down those pertussis cases. Here we have rubella, so we have the first vaccine being introduced in the mid-60s. Then we have the second vaccine, which is the combined MMR vaccine being introduced. And once you introduce those, we get a massive drop in the cases of rubella, which is German measles. Down here we have polio, so there's two polio vaccines. The first one was had to be injected. The second one was an oral vaccine, which you just take a sip of a liquid. When the injected one was introduced, we see this massive drop, and then when the oral vaccine came in, we get this huge drop down to pretty much close to 0 cases worldwide now. We almost eliminated polio from the earth. Here we have measles, so again, the first measles vaccine, and then the MMR, which we saw, where the MMR is over here. Again, as soon as the vaccine is introduced, we see these big drops in the number of people getting, in this case, measles. Finally, we've got diphtheria. Again, so we can see the number of people dying from diphtheria dropping over time before the vaccine is introduced, so that's through just good medical care. Then as soon as you get the vaccine introduced, you get this sharp decline, down to almost no cases. So we can explain acquired immunity with what we call the primary and secondary immune responses. So the primary immune response is when you're initially exposed to the pathogen. Now there's a delay from the initial exposure to you starting to produce antibodies, and that's what we're measuring on the y-axis here. So as your body starts to produce the antibodies, you'll still feel sick, but eventually you'll get better because the antibodies being produced are going to inactivate the pathogen. And then the amount of antibodies decreases because you're not producing as many anymore due to the infection. So this is where you have antibodies still floating around your system, and you've also got your memory cells floating around your system as well. Then if you're exposed again, you can get a really fast production of antibodies because you have both the memory cells and the antibodies already present in your blood. So you get this huge spike in the numbers of antibodies. So this means that the second time you're infected, you might not even feel ill at all because your body just produces those antibodies really, really quickly. So you might not even feel sick. So today on Flipping Science, we looked at acquired immunity in a bit of detail. That's it for Flipping Science today. See ya.